Okay. Now, one of the interesting things that's one of the very interesting things is that if you've got a carbonyl compound, and typically these are ketones, esters, and amides. And it's probably more popular with esters and amides, to be perfectly frank. But the protons that are on the alpha carbon are relatively acidic. Relatively acidic. And so what can happen is that they can be deprotonated if you use a strong base. And the one that I will talk about the most is this. LDA. So lithium diisopropylamine. And so these reactions are typically carried out in THF or diethyl ether at minus 78 degrees. So this is basically acetone and a dry ice. Some of you will already used an acetone dry ice bath in the lab. For the rest of you, we'll be doing that in the second experiment. And so what happens when the protons get deprotonated is if we'll draw a little mechanism here. So electrons grab proton, electrons move up to the oxygen, and we end up with, I'll call this R star. And we would call this a lithium enolate. A typical enolate, which we would have seen before, is just with a negative charge here. But lithium enolates are actually stable at minus 78. So it's a relatively stable enolate. And if we draw a resonance structure of an enolate, you see something interesting, and that being that what we end up with is a carbon with a negative charge. So this carbon is a good nucleophile. So this can be a nucleophilic carbon. There's certain instances where the oxygen's actually the nucleophile, but more often than not, I guess we could get into that a little bit later when we do some of the syntheses. It'll be it's mostly the carbon that's a nucleophile. So this is a nucleophilic carbon, and it can attack other electrophiles. So things like, so we've got let's draw this here. So if we're thinking of SN1 type of reactions, it would be for alkyl halides, it would be things that are good for an SN2 reaction. So if we're talking about alkyl halides here. So this would be things like, I don't know, a primary, if we had, so primary alkyl halides, we could have like methyl or other reactive electrophiles like, say, an benzyl bromide or an allyl bromide. These are all really good carbon-based, like alkyl halides. So these are all really good in SN2 reactions. So that's one really useful application for this, is that these electrophiles that are good for SN2 reactions, it reacts well with them. It doesn't react well with, like you would have be very hard pressed to be able to do a reaction using, say, a secondary alkyl halide, because you're going to get a lot of elimination products with this. So there is certain limitations to that. So this one, it wouldn't be particularly good, but these other ones, it would be really good. So in the lab, that's what we're doing. We're going to be using, well, in the first lab, we're using a stabilized enolate to react with this guy. Now, that's not the only reaction that can take place here. And in fact, I should, like, you might ask yourself, well, how does this lithium get on the oxygen? What tends to take place is that there's a cyclic transition state here. I'll draw this lithium in. Color this because it's sort of like a complex. But anyway, when you remove the protons, like this grabs that, these electrons go here, that electron goes there. Or we could even do it like this. This is probably better. This. I better draw in my other set of lone pairs. And so, yeah, that's how you basically end up with your lithium enolate R star. Now, the other reaction that this is really good at, besides those reactive alkyl halides, is in what we would call the, well, let's do one other thing too, actually. Okay, so lithium enolates are stable at minus 78 degrees. And there's lots of reactions you can carry out minus 78 degrees, but sometimes you want to actually preserve the enol structure, and there is a stable enolate equivalent, excuse me, that can be worked with at high temperatures. And that is what we would call a silyl enol ether. And so the way you make these and what this looks like is you have your lithium enolate and you react it or quench it with trimethylsilyl chloride, and this is what you end up with. So, yeah, and this is essentially a It's almost like an SN2 reaction. These electrons go there and that departs. The silicon-carbon bonds are quite long. The silicon-chlorine bond is quite long, so it's not quite as sterically hindered as a typical SN2, which would be impossible with 3 alkyl groups there. But yeah, so the result is that you've made a silicon-oxygen bond, and these things are stable at room temp. They're not particularly stable in water, though. So you basically want to avoid water. Because under acidic conditions and basic conditions, this can be hydrolyzed. So that's just one of the caveats. So you would basically, you'd make this and then you'd evaporate the solvent to have this stable equivalent. Yeah, and so actually this is a good there might be one obvious question is, okay, so if I'm reacting my lithium enolate with trimethyl chloride, so this attacks with the oxygen. Why does, if you're reacting with an alkyl bromide, why does it attack at the carbon? So the carbon end of the enolate, let's draw, I'll move somewhere. So this is there's basically 2 parts that can be reactive. The oxygen side tends to react with hard electrophiles. And the carbon side tends to react with soft electrophiles. Now, what is hard and what is soft? When you guys did inorganic chem, you would have talked about hard and soft Lewis bases, right? So what's the best? So does anyone remember what their definitions of hard and soft was with regard to inorganic chemistry? Okay, let me, what's the inorganic version of hard and soft? Okay, so so species that are polarizable, I guess, I would tend to classify these as soft. And in fact, so when we're talking about hard and soft Lewis acids and Lewis bases, you can have a hard Lewis base and a soft Lewis base, or a hard Lewis acid or a soft Lewis acid. So things that are lower on the periodic table tend to be soft. So if you've got a carbon which is bonded to a iodine, let's say this R. So iodine isn't particularly electronegative, but it behaves like it is because it's polarizable, and its electron sphere can be easily distorted by the solvent and things, which means that this little carbon that it's bonded to will have a delta plus, and this would have a delta minus, but it's not because of a strong electronegativity difference. So if you had, say, carbon bonded to a fluorine, there's this really strong sort of electronegativity difference, which would be delta minus, and this carbon would have a delta plus. But it's because of that, because fluorine's such a really strong electron withdrawing group. So soft electrophiles would be carbons that are bonded to iodine or carbons that are bonded to bromine. Other soft electrophiles, like those are two examples. A hard electrophile are species that are dominated by, so if we're talking about soft electrophiles, molecular orbital theory would be important. So this would be homo-LUMO type interactions. With hard electrophiles and hard nucleophiles, this would be electrostatic, basically, interactions. So there's a negative goes to positive, that type of stuff. Now, it just turns out that silicon tends to be a hard electrophile when it's reacted with oxygen. So the silicon and oxygen form a really strong bond. A silicon fluorine interaction would be a hard, soft sort of, sort of hard interaction. So the most common sort of interaction where the electrophile is reacting with the oxygen, the one that we'll see the most would be if it was silicon, like a TMS chloride, for example. Another example, I suppose, which you might see is an acid chloride. So this is polarized in this direction. This is polarized in this direction. So that carbon there has got really a delta plus plus. It's quite electrophilic. So acid chlorides would tend to react at the oxygen. And this is quite different than, say, an aldehyde, which is this. These react at the carbon. So, and in fact, the reaction of the carbon with the aldehyde is a very specific reaction called the aldol reaction. Aldol. Now, let me think. Right, okay, so yeah, there's another really important factor, which I guess I should talk about. There's two other ones that we could talk about quickly with regard to enolates. But before I do that, are there any questions? Okay, now there's something special. There's another special sort of thing to think about, and this applies when we're working with ketones. Okay, so let's say that we've got this ketone. There are actually 3 different enolates we could generate from this ketone. Whereas with, okay, so the 3 of them would be as follows. Oh, let's erase this. And I'm just drawing the lithium version of it just for the sake of argument here. So this is what makes ketones interesting, is that there are particularly, I've added a carbon, so we got an ethyl group on one side and a methyl group on the other side. So one of these enolates forms faster than the other, and some of the others are more stable than the one which forms the fastest. So yeah, so one of these is what we would call the kinetic enolate. Call this A, B, or C. So which of these do you think is the kinetic enolate? So the kinetic enolate this would form the fastest.
It's A.
Okay, and why is that?
It's less substituted. Isn't that the reason?
Yeah, so it's less substituted. There's technically, there's 3 protons on that carbon which could be removed. And so, yeah, so A is what we would call a kinetic enolate, kinetic. And B and C we would call thermodynamic. Now, it turns out there's a way to form kinetic enolates preferentially, and there's a way of forming thermodynamic enolates preferentially. And there's even a way to, a way to distinguish between B and C, because these 2 enolates, B and C, when it comes down to doing certain reactions, the stereochemistry of the products could be quite different based upon the geometry of those enolates. So is the carbon here opposite to the oxygen, or is it on the same side as the oxygen? So that's sort of how this works. So kinetic enolates. So if you've got so if you want to form the kinetic enolate, the typical protocol is LDA minus 78. So if we had, say, this compound here, LDA, THF, minus 78, we will form preferentially this compound, this kinetic enolate. If you wanted to form the thermodynamic one, there's a different reaction that you would do. First thing you would use is TMS chloride and a base like triethylamine. And here, what you end up making is the thermodynamic enol ether. And this can be converted by reacting it with methyl lithium, THF, in minus 78, to this. And this would be the thermodynamic one. And the fun part is that if you wanted to make the kinetic silyl enol ether, you would just react this with TMS chloride, and you would have this. So using a combination of LDA or TMS chloride and triethylamine with methyl lithium, or just doing LDA and then the TMS chloride as a quench, you can make all four of these types of stable enolate equivalent. So, and the other part, which I haven't really gotten to, is that the silyl enol ethers have a completely complementary sort of reaction profile. So they're good at SN1 type electrophiles. So things like a tert-butyl carbocation would or the carbocation of name is escaping me here. This tert-butyl carbocation would react with the silyl enol ether. It wouldn't react like with the LDA. That would be a total mess. So it's a completely different. But this isn't really important for what we're doing in this class. But it is a complementary type of electrophile. The key point, though, is that you can make both types of. You can make the silyl enol ether, the thermodynamic, or the kinetic, and you can make the lithium enolate thermodynamic or kinetic just by the way you manipulate the reaction conditions. So with ketones, it's really interesting that you've got two sides that could react depending on how you want to do it. With the esters and the amides, there's only one side because there's only one type of proton here. So with the amides, you have to make sure that there's no hydrogens on the nitrogen, but you know, LDA -78. Then you are going to generate your enolate. And there's only on one side. Same thing with the esters. So if you had RME, you will generate the ester version of the enolate as well. Okay, so that was what I wanted to get with regard to that. So that's basically how you make them. Later on, we'll talk about this part here, the varying geometry between the two. We'll talk about this a bit later. In organic 3, we did, in advanced organic OChem, we did a bit of stuff on this, but we'll get to that later on when the time comes. Now, I guess the key reaction that we want to talk about is the aldol reaction. So if you've got your enolates and you react it with an aldehyde, the following transformation takes place. So this will basically complex with the lithium. This is kind of neat. It's a cyclic transition state. And as these electrons move here, these electrons move here, those electrons basically move up. Or you can move them onto the oxygen, technically. I guess that's what Dr. Yan would say. And you end up with this. And if you acidify this, which you'd want to do, add H+, you will have this. And if you wait too long, you can actually get a dehydration reaction taking place. So this is if you leave it too long and things go awry. But you end up with an enone. But it's the actual aldol product here that we're really interested in. So you will notice that the carbonyl is basically 3 carbons away from the alcohol. So aldol basically comes from aldehyde alcohol. So you start with an aldehyde and you end with the alcohol. But this also works with ketones too. So it's possible to do the with unhindered ketones, I guess would be a better way to do it. So this reaction works really, really well with aldehydes. And if you've got if you look at and we'll see this when we do our some of our syntheses, you'll notice that many natural products have a repeating sort of 1-3 relationship with 2 oxygen bearing carbons. So it could be something like this, or it could be something like this. And of course, we've got some chiral carbons here, which I'll just star in red here. All of these carbons could potentially be chiral. And there's a way of actually controlling the relationship between all of these various functional groups, depending upon how you carry out the reaction. So yeah, I'd hate to think of the number of man hours that have gone into research with regard to the aldol reaction. But one of the things that's really interesting is that, I know we'll do this, right? We'll do this just as an example. And we'll just look at, so the way, this is actually, when we're doing the aldol reaction, it's actually a cyclic transition state. So let me remember how I used to draw this. Right. Okay. So if you ever need to draw a cyclic transition state, it's always best to start with a chair. Okay. And so we are going to oh no. Okay, let me remind everybody. We've got our 2 partners are going to be Now I've drawn a little squiggly line with regard to this methyl group here, because this methyl group is going to be the methyl group here or the methyl group here. And I just want to show that depending upon the geometry of that methyl group, you're going to get different products when this thing is all said and done. So we are going to do one example where, oops. That's like this, and the other example where it's exactly the opposite. So we're going to be making a bond there, and we're going to be making a bond here. That loosely looks like a chair. This other one, this actual one looks better. So let me erase this. Okay, now I haven't added this R group here yet. Because I want you to tell me where to put it. So there's two basic positions where I can put the R group. And I'm going to draw it in blue or something. Okay, so I could draw it green here. No, that's not what I want to do. Okay. I could draw this R group up and have the H like this.
So like
or I could draw
the
this.
chair conformation thing, where it's like either vertical or horizontal.
Right. So yeah, so I could put these are the two basic options I could have. The one in red or the red one in green. So there was destabilizing interactions in our chairs, and those destabilizing interactions happened when you had groups that were
Axial.
axial. So if you had an axial group here R and an axial group here R, there was basically that steric interaction, which was that 1,3 diaxial interaction. So this chair would flip and it would look like this. So the two R groups are still both up, but there's not that diaxial interaction. So one of these two chairs has got a diaxial interaction taking place, and that is this one here, right? So this would not be the favored transformation. When we do this reaction, because this R star group is always axial, this chair is the favored interaction. And what happens is that when we make all of the bonds, this is kind of hard to, I'm going to draw this as a zigzag here. R, H, O, H, O, R. So the methyl group is here and the OH is back over here. Now, what this translates to, if I was to draw this sideways, this translates to methyl group forward, OH backward. So the methyl group and the hydroxyl group are on opposite sides, so it's basically anti. Now, how did I translate this in such a fashion? Okay, so let me direct you to this part. So this bit in this highlighted thing in yellow is a zigzag, and I'm basically drawing that same zigzag on the other molecule here. Now, if your eyeball is here looking at it, so we're looking at it from this direction, because that's the perspective of what we're looking at over here. You will notice that on the zigzag, certain groups are pointing towards you. One being the methyl group, because it's on this carbon, it's pointing towards us. The other group, which is pointing towards us on the carbon next door, this H, that's really dark. Let me erase that. This H is pointing towards us because the OH is pointing, is on the opposite side. It's way over here, right? So the methyl group's forward and the OH group is behind. Now, and if we were to do the same, we're gonna run out of time, but if you do the same, if you draw the same chair for here, the same sort of transition state for this one, the only thing I've changed is that I've put this methyl group, which is way over here on the same side as the R star. I've now placed it on the same side as the this O lithium. It's over here. And so when you do get the same product, you'll see that the methyl and the OH are on the same side. So there's two different ways of making aldol products, and it's based purely upon the geometry of the starting enolate. Is the starting enolate like this, or is it like this? And it changes the stereochemistry. Is the methyl group forward or is the methyl group backward? We'll, I sort of, sorry, this part here, I sort of really try to draw this no, erasing everything. Oh, yeah. Anyway, the thing I don't like here is that this black line is, there we go. Let's make this, it's in front of it. Like this is in front. Try to draw the product of this and you'll see that you end up with the two groups being on the same side. But anyway, we're, yeah, so as I said before, like you could do a whole class just on enolate stuff, but I wanted to show you, just highlight some of the highlights of it. But we're gonna see a bunch of aldol reactions in the coming part of the course. So when we talk about here, this little, these disconnections here, 1, 2, 3, ketones, esters, amides, aldehydes, and you can get this similar sort of 1, 2, 3 fragment from that. This is such a small little part of a little slide here, but there's just so much chemistry that can be associated with it. It's really amazing. And yeah, so that's part of the, there's just so much there. Anyway, so what we'll do next class is we'll talk about clays and condensations. Again, the last little bit's a lot of enolate chemistry. And it's funny, the best one for this is esters. You get less side products from it. But anyway, it's 12:31. So some of us have got lab in about an hour and change. So I've got to get to the university there. So I'll basically sign off now. If you've got any questions, do you have any questions immediately? If not, we can discuss this at the start of Thursday's class.
I guess the thing to remember is that if the enolate is like cis double bond, then the resultant 1,3 is going to be the same side, right?
Right. So that, yeah, that only, yeah, that's, yes. And so on carbon 2 here, which I'm sort of circling, yeah, if there's ever a substituent there, like a methyl group or something like that, yeah, if you're going to do this reaction through an aldol reaction, then there's a couple of things you need to control. But if there is nothing on carbon 2, then it really doesn't matter because there is no stereochemistry there. But right, if you've got these types of enolates, will give cis, whereas the other ones will give what we would call anti. We call it syn or anti. Now, the other interesting thing is that the way I've drawn this, it would be this thing plus the enantiomer of it. They would either be both forward or both back. And this one would be plus the enantiomer, which the people which took organic 3 discovered that there's actually a way of controlling which enantiomer you get too. So there's a whole bunch of really fascinating stuff we could do with that. But anyway, because this sort of structure is common in natural products, people devoted a lot of time to sort it all out. Oh, the joys. Okay, so I will see everybody on Thursday, except for those of you who I will see later on today.
Do we need to bring anything again for lab?
Lab coats. Do you have your little lab sheet with
Yes, I do. Yeah.
your calculations and stuff? Just that. We got lab glasses there. That's about it. So just your lab coat and just so you know all your quantities and that type of thing.
Sounds good.
Alrighty. Super. Okay, well, I'll see
Bye.
you soon.
All right. Thank you, Dr. Hill.
You bet.
Thank you.
See you.